The universe is dying. I know that sounds intense. We spend so much time looking out at space, searching for life, watching galaxies crash, and seeing new stars ignite. We think of the cosmos as endless, full of fire, growth, and action. But every single thing in existence, every star, every planet, every force, is currently following a path that leads to one simple end: total, inescapable darkness. Everything we see is locked into a countdown where the final answer is zero. The question isn't if the universe will end, but how. And what happens along the way is stranger and far longer than you can imagine. We are talking about timescales that make the 13.8 billion years since the Big Bang look like a quick coffee break. So, how does the cosmos actually die? Let's look at the basic rulebook of existence that writes this ending. The final fate of the universe is ruled by something called entropy. You might have heard of it. Think of entropy simply as the universe's tendency toward messiness. It's the reason why things break down, why your room gets dirty, and why hot things eventually cool off. Energy likes to spread out and become less useful. That's entropy at work. The funny thing is, the universe started off in an extremely tidy state. Roger Penrose, a really smart physicist, actually looked at the odds of the Big Bang starting so ordered by chance, and the probability was ridiculously tiny. We are talking 1 part in 10 to the power of 10 to the power of 123. The early universe was arranged very neatly, like perfectly separated colors of paint waiting to be mixed. But ever since that beginning, the universe has been unwinding. Tidy energy turns into spread out, messy energy. Useful energy turns into unusable waste heat. This flow from order to mess is a one-way street. It only moves forward in time. This is the whole engine driving the collapse of the cosmos. Gravity tries to pull things together, making structures like stars and galaxies, but entropy is slowly turning all that highly focused, useful energy into spread-out, low-grade heat. If entropy wins, and science says it always does, the universe must reach a state where everything is completely messy and uniform. All the useful heat is gone and nothing new can ever happen again. This final, cold, inert phase is what scientists call heat death. It's the ultimate cosmic deep freeze, but this isn't a quick process. Before the universe reaches this ultimate heat death, it has to go through a long, quiet middle age where all the amazing structures we see today, the stars, the galaxies, and even the black holes, have to vanish first. The fate of stars and galaxies is bound up in 2 key processes: the great separation of matter and the exhaustion of fuel. First, let's talk about how the vast structures in space pull apart. We see galaxies grouped together in clusters, and sometimes these clusters crash into one another. For example, our own Milky Way is speeding toward the Andromeda Galaxy, and they will collide and merge in about 4.5 billion years. This happens because they are close enough to be connected by gravity. But outside our local cosmic neighborhood, the picture changes entirely. The universe is expanding. We know this because when astronomers look at distant galaxies, the light coming from them is shifted toward the red end of the spectrum, a phenomenon called redshift. This isn't just galaxies moving through space, it's the space between them stretching out, carrying them away from each other. As the universe continues to expand, driven by forces like dark energy, this separation accelerates. Galaxies that are not already bound together by gravity will fly apart, eventually moving faster than light relative to us. Now don't worry, this doesn't break the speed limit in space, but rather that the space itself is stretching faster than light can cross it. The consequence of this accelerating separation is that billions of years from now, our descendants, if they exist, will look out into the night sky and see almost nothing. All those countless galaxies visible today will have retreated beyond the cosmic horizon. The Milky Way will become an island universe, isolated in an ocean of dark, empty space. No more massive collisions to fuel new activity, just isolation. Second, the fire must go out. Stars eventually stop forming because they rely on a finite fuel source, hydrogen gas. Stars spend most of their lives converting hydrogen into helium in their cores. This fusion releases the massive amounts of energy that make stars shine. This phase, known as the main sequence, lasts for billions of years for a sun-like star. When stars die, they eject some of this processed material, the metals astronomers call everything heavier than helium, back into the surrounding gas clouds. This recycled material helps build the next generation of stars. But this cycling process cannot last forever. Every new star burns up hydrogen. Over vast timescales, all the usable hydrogen gas in the universe will be fused into heavier elements. Without this gaseous fuel, new stars can no longer be born. The fire fades slowly, though. While big, hot, massive stars burn out quickly, sometimes in just millions of years, smaller stars live incredibly long lives. The small, faint red dwarf stars, which are the most common stars in the cosmos, burn their hydrogen fuel so efficiently that they can live for trillions of years, long after the last massive star has exploded and the last galaxy has drifted away. But even these tireless red dwarfs will eventually use up their supply, fading first into dim white dwarf remnants and then cooling completely into inert cold objects called black dwarfs. The universe is not old enough for a single star that has formed to have cooled down enough to become a black dwarf yet. But in the distant future, these stellar corpses will be the most common objects in the cosmos. Once all the fuel is gone and the stars have faded, the universe will be populated mostly by these dead stellar remnants and the even stranger things that remain, black holes. If stars and galaxies vanish through fuel exhaustion and separation, what about the most stable things we know, black holes? Black holes are formed when extremely massive stars collapse, concentrating a huge amount of mass into an infinitely dense point called a singularity. They are defined by the event horizon, the point of no return from which not even light can escape. You might think that a black hole is an eternal prison, designed to suck everything in and hold it forever. But even the ultimate cosmic devourer cannot escape the tyranny of entropy. Black holes evaporate. This idea, known as Hawking radiation, comes from combining the rules of gravity with the strange rules of quantum mechanics near the event horizon. Here's the simplified picture. The vacuum of space is not truly empty. It is constantly buzzing with activity, where pairs of virtual particles are created and then almost immediately destroy each other. They pop into existence and quickly vanish. When this happens right at the edge of a black hole's event horizon, things get weird. Imagine a pair of these particles popping up right at the horizon line. One particle falls into the black hole and the other escapes out into space. The particle that falls in has negative energy relative to the outside, while the escaping particle carries away positive energy. This process means the black hole is effectively losing energy and mass to the universe. It is radiating mass back into space, turning mass into light, photons. For every particle a black hole sucks in, it eventually spits out radiation in return. This is Hawking radiation. For the massive black holes we see today, including the supermassive ones millions of times the mass of the Sun, found at the centers of galaxies, this evaporation process is incredibly slow. The incoming matter and energy they absorb from space is far greater than the tiny amount they radiate back. Astrophysical black holes are, for all practical purposes, currently stable objects. They can grow, but they do not evaporate much. But imagine a time far in the future, billions of years after the last star has died, when the universe is cold and empty. There is no gas left, no stars shining, and nothing falling into black holes. When this feeding stops, the black holes are left alone, and the slow, steady process of Hawking radiation takes over. The speed of evaporation depends entirely on the black hole's mass. The smaller the black hole, the faster it evaporates. A black hole with the mass of our Sun would take about 10 to the 67th power years to disappear. That's a 1 followed by 67 zeros. That timescale is so absurdly long that it defies comprehension. But the real monsters are the supermassive black holes, the ones that anchor galaxies with masses up to 1 billion times the mass of the Sun. These behemoths take vastly longer to evaporate. A black hole of 1 billion solar masses would take an astonishing 10 to the 100th power years to fully vanish. To put that number into perspective, the smallest stars haven't even faded yet, and we are already talking about trillions of years. Now we are talking about a number that makes a trillion look like a single grain of sand. This is the time until the universe becomes pure darkness. We have arrived at an era often called the degenerate era, where all star formation has ceased and the universe is populated only by dead stellar remnants, scattered planets, and massive black holes waiting patiently to fade away. This era begins about 10 taken to the 14th power years from now, 100 trillion years into the future. The lights are officially out. The gas clouds needed for starbirth are gone, having been used up long ago. First to cool are the white dwarf remnants, the superdense cores left behind by sun-like stars. Currently, white dwarfs are incredibly hot, but they lack fusion fuel. They slowly cool and fade, taking close to 1 trillion years to drop below the temperature of the sun's surface. Once they reach this final cold state, they become black dwarfs, dense, Earth-sized blocks of carbon and oxygen that emit no light. During this immense wait, the matter itself is under attack. The small, faint red dwarf stars, the ones that lived the longest due to their careful consumption of hydrogen, are finally running out of fuel around this 10 to the 14th power year mark. They puff up slightly before collapsing into their own kind of low-mass, cool white dwarfs and begin the long, trillion-year fade to black dwarfs. By the end of the degenerate era, the universe is a dark, cold graveyard filled with these black dwarf stars, neutron stars, and brown dwarfs all moving quietly through the void. The few planets that survive stellar deaths are frozen, orbiting these inert masses. But even this collection of cold remnants cannot last forever. In the utter blackness, the remaining matter is constantly subjected to weak gravitational pulls. Over time, scales far surpassing the age of the universe thus far, orbits decay, and objects occasionally collide. Think about the quiet chaos inside a now isolated galaxy like the Milky Way. Black dwarfs and neutron stars, slowly moving in the dark, experience close gravitational encounters. These encounters act like a cosmic pinball machine, scattering objects outward. Some objects gain enough speed to escape the galaxy entirely, drifting away into the expanding void. Others lose energy and spiral inward toward the supermassive black hole, still lurking at the core. These close passes, happening over eons, lead to the galaxy slowly dissolving. The last remaining stellar corpses are either ejected into the intergalactic darkness or consumed by the central black hole. But the final act of this era is the longest, waiting for the massive black holes themselves to disappear. As we discussed, a supermassive black hole with 1 billion solar masses takes 10 taken to the 100th power years to evaporate through Hawking radiation. This time is so long that the remaining matter in the universe must endure unimaginable longevity. This is where the universe enters the true blackness, the era where the only activity left is the slow, steady process of decay, driven purely by the quantum mechanics of the void. The timescale we are discussing now, the black hole era, is so vast that matter itself is barely recognizable. Around 10 to the 40th power years from now, one followed by 40 zeros, long after the stars have faded and most structure has dissolved, another profound shift occurs. Up until this time, we assumed that protons, the foundational particles that make up atomic nuclei, are stable. But according to some models of physics, protons might actually decay, meaning that normal matter slowly breaks down over extreme stretches of time. If this happens, all the remaining matter, the black dwarfs, neutron stars, and scattered planets, will slowly dissolve back into light and much lighter particles such as neutrinos and positrons. Imagine the entire mass of a dead planet dissolving, atom by atom, over billions of years until all that remains is a thin soup of elementary particles. In this universe, the only objects left are the massive black holes, patiently radiating away via Hawking radiation. They are surrounded by a vast, cold expanse where particles struggle to find each other. The temperature of the background space drops toward absolute zero. Gravitational wave signals, which are oscillations in the fabric of space and time, fade away almost completely as sources of gravitational activity, like merging black holes, become incredibly rare. For trillions upon trillions of years, the black holes radiate. The energy they emit, the Hawking radiation, is extremely low frequency, mainly photons and lighter particles. Finally, once the black holes have lost almost all their mass, their temperature actually starts to rise rapidly because smaller black holes radiate faster. In the last moments of a black hole's existence, it radiates away with a final, tiny burst of high-energy particles before it is completely gone. The disappearance of the largest supermassive black holes, taking 10 to the power of 100 years, marks the end of the black hole era and the start of the dark era. The final moments of the cosmos arrive when entropy has reached its absolute maximum. This is the era of true heat death. The universe will be almost perfectly uniform, extremely cold, and completely dark. There are no energy sources left to perform any useful work. Gravity, the force that built all the beautiful structures we love, the stars, the planets, the life, has essentially lost its purpose. All that remains is a thin, cold broth of photons, neutrinos, and light particles, drifting ever farther apart due to the ongoing expansion of space. Even these faint particles are stretched by the expanding space until their wavelengths are too long to interact with anything. The cosmos becomes a deep, silent freeze. There is no warmth, no light, no structure, and no change. Nothing to see, nowhere to go, and nowhere to hide. This is the ultimate victory of messiness and decay. But hold on a second. We're still here, right? Orbiting a beautiful, fiery star on a planet that is constantly protected. And what keeps us here, safe from the chaos of space, is a different kind of protection. One you never even think about until it vanishes. The cosmic picture we just painted is intense, a future where all the light fades, galaxies become ghosts, and even black holes dissolve away. Everything in the universe, from the largest galaxy cluster to the smallest particle, is rushing toward this ultimate cold, dark destiny. But for us right now, our existence is protected by forces working hard to fight the cold fate of the cosmos. Think about the planet beneath your feet if you want to understand space like a NASA-level analyst. Quick, without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. Earth has been a safe harbor for billions of years. We talk about the sun's fire and Earth's gravity keeping us alive, but there is one invisible shield, one fundamental force that ensures we are not blasted away into the vacuum of space. This shield keeps our atmosphere locked in place, protects us from deadly solar winds, and guides the direction of human survival. What if that shield suddenly failed? What if that force that wraps around our planet, that stops us from being exposed to the harsh reality of space, just vanished? It would be the end of our world as we know it, not in 10 to the 100th power years, but instantly. To see exactly how fast that shield could fail and what would happen if our home lost its most important protector, click here to this video. What if Earth lost its magnetic field video? I'll see you there.